4x cubed minus 24x squared. You can factor out a 4x squared, leaving you with x minus 6. So x equals 0 and x equals 6 are possibilities of stationary points. And if we check a value before 0, like -1, we're going to get negative, so it's decreasing. If we check a value between 0 and 6, like -3, it's still negative, so it's decreasing. And after 6, we're going to have it positive, increasing. So that'll help us with our first derivative test when we go to explain what the points are. So I'm going to leave the explanation and leave the points for now. We're going to also do our second derivative over here, which will give us 12x squared minus 48x. Make that equal to 0. Factor out a 12x, leaving us with x minus 4. So x equals 0 and x equals 4 are our points where we could have an inflection point. And if we plug these in, 0 and 4, a value before 0, negative times a negative would be positive. Make our little cyclops here. There we go. And between 0 and 4, like 2, you're going to have a negative value. And then afterwards, a positive value again. So, for local mins and local maximums, here's our first derivative test. Okay, from the first derivative test, we know that 0, 0 is a stationary point of inflection because f prime of x is decreasing before x equals 0 and decreasing after x equals 0. Okay? From our first derivative test, we'd also know that 6 comma, and has someone plugged that in? What do you get? Oh, I was going to guess 5. Okay. Minus 432. We know from our first derivative test that that is a local minimum. Because f prime of x is decreasing before x equals 6 and increasing f prime of x is increasing. Oh, I should, just a second here, I shouldn't write decreasing. F of x is decreasing, f prime of x is positive. So we can either write f prime of x is positive, which means f of x is increasing. For the last one, so you don't have to change your notes, just scribble out that f prime. We can say f of x is increasing before x equals 0 and decreasing after x is 0. Here, I'll actually use f prime of x, and I'll say it's a local minimum because f prime of x is greater than 0 before x equals 6, which implies that the function is increasing, and f prime of x is less than 0 after x equals 6. The function, f of x is what's increasing and decreasing because the derivative is either positive or negative. So that's our first derivative test and how we could write it out as an explanation. And I've sort of given two different ways that would be accepted. If you could talk about the original function being increasing and decreasing, or you could talk about the derivatives being positive and negative. Okay? For your second derivative test, The second derivative test is only for maximum and minimums, and since we only have one minimum here, we could say that 6 negative 432 is a local minimum because f prime at 6 is equal to 0 and f double prime at 6 was greater than 0. Or is it less than 0? So what did I say? Yeah, f prime at 6 is greater than 0. So that makes it a local minimum. Yes?
See, like on the first derivative test,
Yeah.
if you would say f prime of x is increasing, would this then also mean that it could be negative just with a positive slope?
So if f prime of x is increasing,
Yeah, this would mean that it also could be negative in that position just with a negative, with a positive slope.
you could say those kind of things, but as far as the explanation goes, it's better to talk about for the first derivative test that, the function is increasing or decreasing, and that the derivative is either positive or negative. As soon as we start to say that the derivative is increasing or decreasing, that's telling us whether it's concave up or concave down. So the second derivative test, you can only say that about that one point, because the other point is an inflection point in that the second derivative test is just about maximum and minimums. We can tell from our second derivative that 0 is an inflection point because it changes concavity at that point, but we don't have to say the second derivative test is not about concavity, it's about maximum and minimums. By the way, our 2 points here are 0, I'll do them in green, 0, comma 0, and 4, comma, negative 256 or positive? Negative 256. And these are both inflection points. So now we've got this wonderful data. Just going to look back up here. We've already got our y-intercept at 0, 0. This one, is it an easy one to find an x-intercept? It actually is, because you could take your original function and factor out an x cubed, leaving you with x minus 8. So, well, obviously, since we already know 0, 0 is a point, it's an x-intercept and a y-intercept. But we also know that x equals 8 is another x-intercept. So when we can find our other x-intercepts without our calculator, we will, just to make our graph even more accurate. So now when we go to graph this one, all right, the biggest number I have is 6, negative 432. So I'm going to go 1, 2, 3, 4, 5, 6. Negative 432 looks like it's right there. And that will set my scale for everything else. So now my next biggest point was an inflection point at 4, negative 256. I actually want to make this just to match. I'm going to make that blue, because I did my first derivative in blue. My inflection point I'm going to do in green. Negative 256, okay? If you come with a ruler, you would find out that that is perfectly placed. 4, negative 256. We also know 8, 0 was an x-intercept. Our other point that's important, which is both an inflection point and a stationary point, is 0, 0. And we know that it is, for drawing it, choose purple for my final graph, concave up here, concave down, and then concave up. So there's our final graph. Oops. Got to get that green point. Oh my goodness. There we go. Sorry, got to make it perfect. Nice. So there's our final graph. Yes?
So if you want to find on our graphs the points of inflection and the min and maximums,
Yeah.
then the second derivative test would be faster.
Yeah, if you wanted to find without having to plug in things, and you're going to do the second derivative test anyways, because you can see it right there, that saves you a step. And then you can just say a little explanation. And actually, the explanation is easier too, because you don't have to talk about increasing before, decreasing after, and those kind of things. So the second derivative test is a little bit cleaner as far as writing things down. As a visual, though, I find the first derivative test is a really nice visual, especially if you add the arrows. I've seen some people teach it where they just say f prime of x less than 0, f prime of x less than 0, f prime of x greater than 0. And without putting those arrows there, then you really don't get to see what's happening. But with the arrows there, oh, I really see that 0 is an inflection point, that's a stationary point, and 6 is a minimum. That's a pretty nice graph.